the lecture on two-dimensional flow visualization using Hele-Shaw apparatus. Uh, let's start with the demonstration. Here we have a flow visualization. Basically, we wish to visualize the flow to demonstrate how the air moves around any object or any model, and the basic objectives of the flow visualization is to understand the flow phenomena. If there is a flow, oncoming flow over a simple model, what happens to the flow properties around that particular model? Okay, sometimes we need make the bluff body to a streamlined body, or we should understand the flow physics around the body so we can do verify the model with the theoretical results, or we can even make easier measurements for designing. For instance, if I want to have a simple airfoil, I want to introduce some kind of a roughness or some kind of a tail to it, or a attachment to it, so I can increase the lift coefficient kind of. So I should understand what is the flow phenomena around the model, so that will help me in understanding the full flow physics, so I can go for any model or any designing of that particular structure. So here we will look into some basics, which is Hele-Shaw apparatus, which we are utilizing in our laboratory. Hele-Shaw apparatus as an experimental setup, which we can visualize the flow around the 2D models especially, and which can depict whenever the streamline pass of any model, we can able to understand how far the boundary layer is being influenced, where is the stagnation points, where is the separation, and how strong the wake and its vortices are. So this the main objective of the experiment is to understand the following: the boundary layer, thickness, and then stagnation point, separation point, wake, and its vortices. And here we have a simple Hele-Shaw apparatus. Let's understand how the working of this Hele-Shaw apparatus goes on. Here we have a tank, and this is a collecting tank. The collecting tank is initially filled with water, and there is a pump, and water is taken by the pump and delivered to the source tank. And there are two valves connected here. One valve is a drain valve. The other is going to be a modulator valve. And the purpose of these two valves is to regulate the flow coming onto the source tank. And here the source tank serves two purposes. One is the storage of the water, and the other one is to supply the water to the test section at the specified velocity. So the velocity is again controlled by this flow, the valve, the inlet velocity, and again the same velocity is going to influence on the test section. And again we have a dye tank. The dye tank injects a small dye. Here we utilize the blue color dye, and that dye will be injected by means of a small nozzles. There are about 32 sections of nozzles in which each needle will induce dye, and the dye comes near to the model is kept over here, which is called as observation region. The flow past this will be understood, and we look from the top view, and then when the flow goes out of the test section, it will be collected by the drain tank. There are two drain tanks to collect any if you go with the higher notch number, the flow rate will be larger. In those cases, we have to have a quantum amount of collecting tank. So we have a two drain tank, and then drain tank are again collected by the collecting tank. So the water leaking from the drain tank coming out will be collected by the collecting tank. And here there are, if there is excessive pressure, excessive flow, so here the source tank should not overflow. So that's why we have a release valve over here. So when we look at the test section, it somewhat looks like this. Here is a schematic view of a Hele-Shaw test section. When the flow of water is indicated by the black arrow mark, and the flow comes here, and you have a model over here. The flow is still flowing on. When the flow started, we will inject a small dye. Here it's a blue color dye, and when the flow comes here, it's a model mounting area, and the flow past this model will go around the model, and then we can able to understand how what is the flow happening around this particular model in the set section. Now we will discuss the objectives of this experiment. The models are geometrically scaled down to fit with the given apparatus, which we say that if we have a bigger model like a truck or a building, we can if you want to visualize that, we cannot able to keep, we have to scale it down proportionally in all three dimensions, and with much care we can scale it down, and then which should be fit within the observation region. So airfoil and other practical applications such as trucks with deflector has been studied for different orientations, and we have also flow parameters. I will understand what are the flow parameters such as I said, stagnation, separation, and wake region that can be clearly captured for airfoil, and then truck and unconventional building. We are in this experiment we have only three factors, three models that we are going to test. One is a airfoil, a trailer tractor truck, and an unconventional building and different nodes. An unconventional building with zero angle is given for this particular study, and here we can able to go with the understanding of how the Hele-Shaw test works out. Here we can see a streamlined pattern around a simple truck. This is an we call this is an aerodynamic track. All the rough edges, corners are almost straight edges. Whereas this is a kind of a slightly aerodynamic where there is a deflector. When the flow comes here, the flow gets separated. When there is a lot of stagnation because the flow is coming and hitting here. This is from the side view. This is from the top view, and you can able to see the flow getting separated from here and then go ahead, and there's a flow separation. And this you can see a strong vertices. This will induce a drag on the vehicle, and this separation will also be uh, induce drag as well as noise. So we have two components of drag as we discussed in fluid mechanics and aerodynamics, and where we have a pressure drag and there is an induced drag. And we have one more component as we call it as a skin friction drag. Uh, Here you can able to see that extensive regions of turbulence are possible over here, but this is a non-aerodynamic truck. We can able to make it slightly aerodynamic by making this edges to be a rounded edges. The flow gets diverted away from the model, away from the truck here. The flow comes here, it can be easily diverted away from the truck, and behind the truck there are a lot of strong vertices. You can compare these two. You can able to see that these regions are comparatively reduced over here. So we will be looking at one model of a truck. So we will just visualize the streamlines around two trucks in tandem, which is one followed by the other. In this particular, the flow is coming from the left hand side, from this side to this side. This side view of a truck. Two trucks are kept it here in tandem, one followed by the other. So the flow is still going on. Now we have injected that dye. As it approaches the model, you can able to see that flow getting diverted. A part of the flow going below the vehicle, a part of it moving out of the vehicle. Understanding the flow is, the object is there. You can able to see how the flow passed with this deflector here, and it passed over the body, and you can able to see how this flow going here over this region, the streamline pattern, and this wake region, this flow getting separated from the body, and again that flow coming onto the nearby vehicle. In real scale, this distance is 8 meters, and there is a wake behind this vehicle as trailing vehicle as well. We call this a leading vehicle. We call this as a following vehicle, and this is the cabin, and you can see the trailer. The gap between the trailer and cabin is not occupied by any fluid particle. Flow is not occupying this area. This gives us a good idea about the stagnation. The front of the vehicle is having a severe stagnation, and the flow goes over here and again to the back, and there is again a if this deflector is not there, lot of pressure will increase. So more dye is passed to understand what had happened. This will gives you a clear picture that flow is not coming back into this space between the cabin and the trailer. And you can able to see that flow going behind the trailer vehicle leaves it smoothly since it's a low Reynolds number. You can able to see that lot of stagnation here. So more amount of ink is injected to understand where are the flow can reach in this particular vehicle. So now we will look into the top view of the truck. The flow comes here. You can able to see there is a lot of stagnation here. A part of the fluid goes over here, a part of fluid comes behind this way. This section. Since it's inclined at an angle of 5 degrees, so it's not coming as such. So the stagnation, and then here is a separated region. When the vertices come and interact with each other, the obviously the drag of this truck will increase. But in that region before that, there is a truck behind this. So this we call it as a platooning or trucks in tandem. This will help the because this vehicle carries most of the forward body pressure. So this pressure will not be influenced to the trailing truck. So obviously this will have a less drag on the behind the truck, or the trailing following truck will have very less drag. And calibrating the flow velocities, we have procedures like acting with two valves, as we discussed. Two valves are here. Operating with these two valves, we can able to control the flow. By controlling this flow, we can able to get a flow rate of 0.195 meter per second, 0.15 and 0.08. Around that is a flow rate meter cube per second, and velocity is about zero point 0.1 and 0.08, 0.04, and equal Reynolds number is found. We will say that one case of 45 degree will give us a Reynolds number around 4,500, and about 7,500 for a 60-degree opening, and 90-degree opening we may get about 9,500. So we shall able to get this Reynolds number, and here we are going to test everything at a laminar condition, which is 4,000 Reynolds number. And again we can see here, and the airfoil is at an angle 0 degree. The flow is coming over here. The stagnation point is obtained, and then the boundary layer, we can able to see that influence of boundary layer, and there is a separated flow here. There is a wake region, and again we can able to understand that in this case the pressure distribution on top and bottom are almost same. So here you can able to see that a very less amount of lift will be produced. In this case, there is a flow coming here onto this airfoil, which is inclined at an angle 15 degrees. What happens here, the flow coming and hitting you over here will experience a high pressure, and the flow getting separated over here, the separation region is here. So that what happens here is because of the separated flow, there is a low pressure region, and this is a wake region. So low pressure and high pressure, the net resultant force will act in this direction. So net resultant is this way, and the component of lift will be upward, and component of drag will be there acting along the flow. So this can be easily seen that if you travel in a uh, vehicle, put your hands in this way, and you can find a lot of force will drag you back. And sometimes if you incline it slowly to an angle, and you can feel a small amount of force will be acting. If you put it this way, streamlined, and you say that not much force is acting because it's symmetric, slowly incline it until a point you'll get the resultant force is acting like this, and beyond a point you get more drag force rather than the lift force. So we call that particular point as a stall. So here is one more case of minus 15 degree was tested. The minus 15 degree, the airfoil is at a negative 15 degree. The boundary layer is drawn over here. After the separation, there is a reverse flow on the airfoil, and again here you can able to see that stagnation point. But what happens here, the high pressure region is on the top, and the low pressure, because here is a separation, and here is a wake region, and here is a low pressure region. So net force would increase in the downward force. So applications of lift, we need lift in terms of aircrafts, and and again we need a downforce in terms of cars. If you install spoilers, it will increase more traction and downforce to the vehicle. And here is an example of a truck. You can able to see a simple truck which has a flows coming from the side. I can see that stagnation region, severe stagnation. With this shows how this is a non-aerodynamic truck. We can say that not much, the deflector is missing here. So flow separation starts here. In that video we have seen with the deflector, and again the flow moves behind the vehicle, and you can see a strong wake region. And again this is with an angle 10 degree. There is a substantial difference is the flow separation moves little forward, and which is says that 0.934 from the rear end. In this case it's 0.862 length, and the reattachment length is also changed at 0.672. And again here is going to be at 10 degrees. You have negative 10 degrees in the downhill position, and you can able to see that flow separation happens even beyond it. So this is the understanding that when the truck travels with a 0 degree, how the flow field would look like when it is traveling at 10 degree upward up the hill and 10 degree down the hill. The important understanding from this is the flow separation is different for different cases. When it is at 0 degree, you can able to see flow getting between these two, cabin and trailer. Obviously the drag force will be larger. In this case the drag force would be much different, because the flow was not getting much getting into it, and here the flow is not at all getting in between these two compartments. And again this is the one with the deflector. Here without the deflector. With the deflector you can see that the flow field is little uh, until here there is no separation. Here the separation is happening. That's why the big difference is like the deflector can help you in reducing the drag force. And here you can see the flow is coming inside the space between the cabin and the trailer. In this case the flow is not allowed to get in because of the flow going with the higher velocity will go a small amount of fluid could interact over here, and you can able to see due to that we have a separated flow because of the edges. And again this is for a truck with a deflector. And again we can see visualization of truck in platooning at 0 and 5 degrees. Okay, you can see at 0 degree the flow lines we have seen the severe stagnation, the flow behind this vehicle and followed by the following vehicle. This is the lead vehicle, and you can see the flow going away from this strong vortices. And here even non-aerodynamic truck not feeling much drag if you have a following and a trailing. So here is a stagnation point, the separated flow, and there is a wake region. And this is a simple cross section of a building who has this kind of a section, and we can able to see that when the flow comes here, what happens to this surface, the flow gets over here, and then there is a separated flow. There's a severe stagnation because of the frontal area, and there is a rotating vortices, and there is a severe wake. This was a simple roof structure that demonstrates how the flow over any simple building structure. And but basically what we learned over here is Hele-Shaw apparatus can give a fair prediction about relative pressure zones about the structure. With accurate scaling we can get a close relationship between the flow parameters before going on to the actual structures. We also need to understand, we gain more confidence if we have visualized it with Heleshaw or any other apparatus. The flow parameters such as stagnation, separation, wake region are clearly captured for airfoil, trailer truck, and unconventional building at a particular notch number. And we said that stagnation point is found on the leading edge, and angle of attack is 0. Similar pressure distribution on the upper and topper surfaces. Due to camber, there is a small amount of lift force because there is a small difference in the pressure. And when 15 degree is the angle of attack, larger lift we have seen, and when minus 15 degree and this stagnation is moved on the upper boundary, and that's why you have a more downforce than the lift. And truck with deflector is found, stagnation is on the front of the cabin, the separation is seen on the top of the cabin, and the flow moves along the boundary, and the vortex formation can be seen at the back of the trailer, and in the gap between the cabin and the trailer. And again, due to the deflector, the flow is diverted and moves smoothly. And here we saw important thing is deflector plays an important role in reducing the frontal drag. And vortex flow between the cabin and the trailer is avoided. That's very important. And this is a three-dimensional visualization. So if some of cannot able to do, we cannot do it in the Hele-Shaw apparatus. We do it in the internal at our laboratory. So this is the top view of the model. You can able to see the both the vertices coming up at both the edges, shedding of vertices. This is a wake region. There's a severe stagnation at the top of the cube. This is a simple cube. So here we can able to locate the pressure points, trailing edge, and the wake region along the stagnation, along with the stagnation. So this is stagnation pressure. Here is the separated flow. Now we can see the isometric view. So in the isometric view, we can see that locating the three-dimensional vertices. So the vertices shed away from the cube, increasing the Reynolds number. Again, more videos of visualization can be found at our YouTube channel, which you can say that Aerolab PIT Chennai. And I wish to credit all our team members for helping us in making the flow visualization and other activities in our school. So thank you very much, and thank you.